Good afternoon, good evening. My name is Andrew Narvaez, and I am a junior in the Randall Research Scholars Program studying mechanical engineering. Today, I will be discussing my research under Dr. Ludovice, the rational design of cannabinoid extraction co-solvents. So a little bit of background for a couple of the terms that we're going to be seeing. A cannabinoid, for our purposes, is any of the several naturally occurring chemical compounds from the cannabis plant. Most notably of these is THC, but we'll touch on a few other cannabinoids later. A co-solvent is a substance added to a primary solvent to increase the solubility of a compound. And a supercritical fluid is a substance at a pressure and temperature above its critical point. At this point, distinct liquid and gas phases do not exist, but below this point, pressure is required to compress it into a solid. So for our motivation, the application of cannabinoids is growing. Currently, a process randomly extracts these and these mixtures, and the extraction process doesn't reflect how cannabinoids perform optimally in a mixture. So by computer modeling these cannabinoids in supercritical CO2, we will be able to rationally guide experimental extraction to produce more custom, effective mixtures than the current cannabis products. These mixtures can then be tested against numerous pathologies and enhance the growth of the industry. So just kind of to explain it a little better, one mixture currently will attack multiple pathologies like insomnia, fatigue, glaucoma, inflammation. But what we're looking to do is to specify these mixtures to only attack insomnia, only attack fatigue, to make them a little more effective. So this a little bit of background for a supercritical fluid. Many of these compounds dissolve in this high pressure and temperature condition, and that's what we're going to use to better dissolve our cannabinoids. And by adding water as a co-solvent, this will increase the solubility of the fluid. But so for our approach, we are going to be using the MOE software, molecular operating environment. And in the software, we're going to be creating a 3D model box that houses whatever molecule or cannabinoid we are testing with. And surrounded by a supercritical force field, we are going to be running molecular dynamic simulations to kind of see how they react and how they dissolve in the solvent. What we're mostly looking for is these cannabinoids to determine which ones produce the lowest energy state, because these low energy states correlate with a higher solubility. So for my project role, we started off by writing two functions, density and density calculation. Density, all it does is calculate our side length of our 3D cube, because we are taking density as a constant in this scenario. So we are just using density to get its cube length, and then density calc, all it does is check that cube length and make sure it returns the correct density to make sure that everything is working out mathematically. And not pictured is a third piece of code that we're using, which is BoxStart. BoxStart, all it does is load up this 3D cube into the molecular software, which you'll get a better idea of what it looks like in this next slide. So this is what it looks like when we're running these simulations. Here's a picture of a 3D cube with a bunch of CO2 molecules inside. There's a bit of a close-up for the CO2 molecules. But how we started off with this is by putting them all in a gas phase. And what we were really looking for is to recreate some experimental results. And we were just tracking three variables: pressure, temperature, and energy. And we started off by just modeling with these CO2 molecules because we wanted to make sure that our supercritical force field was accurate enough to be able to be tested with actual cannabinoids. So initially, our results proved to not be as close to experimental as we had hoped. Like I mentioned before, we were measuring by tracking energy, which is that first graph, temperature, which is that second graph, and pressure, which is our third graph. All we're really looking for is for the energy to be negative and constant, our temperature to remain constant, because that's one of our variables that we chose to keep consistent, and then our pressure, we were just looking for some sort of equilibration towards the end, which, as you can see, it starts off a little rough, but the pressure does get pretty stable by the end. But here's a bit of a better visual to understand why these initial results weren't what we wanted. The black dots on the graph represent the kind of estimated points from the graph on the left that we are using as our basis, and then the blue dots are simulated results. And as you can see, the black dots represent exhibit a linear positive trend, which is what we want, and then our blue dots, our simulated ones, show just absolutely no trend at all. They're negative, they're sporadic, they're all over the place. So because of this, we realized that we were probably neglecting this electrostatic potential that should decrease at larger distances due to a dielectric effect. And I'll explain this effect a little better here. So this capacitor shows that the charged molecules rearrange themselves in response to the charges they are in between. This shields the electric field and reduces the electrostatic interaction. And the schematic shows the hyperbolic function for electrostatic charge should be scaled at larger distances. The gas phase that we've been using to run these simulations does not account for this large distance, but the distance-dependent dielectric condition and a reaction field condition do a better job of accounting for a larger distance and this dielectric effect. So we realized we would have to probably run some simulations with this as well. Here on the screen you see two graphs. The graph on the left shows our 4 different conditions that we've come to. The blue line represents our experimental results. The yellow line represents a new simulation with a R field. The green line represents a distance-dependent dielectric simulation, and the black line represents our original simulated results. The graph on the right takes out the simulated results so we can get a better close-up look at how this reaction field and this distance-dependent dielectric affected our simulation. But as you can see, by the end of it, the R field tend to be the best model to use for our simulation, just because that one did have a sort of linear trend and it was completely positive with all the pressure values. So past this point, once we got here, we realized that while the pressure values were reaching our experimental, it wasn't exactly what we needed. So we realized we needed to tweak sigma and epsilon of our supercritical force field. The sigma and epsilon values directly relate to our pressure and energy values and how those react. And because we are tracking pressure and energy, we tried to also track enthalpy, or rather the difference in enthalpy between these different densities to kind of see how they would react to the change in sigma and epsilon. So the graph on the left shows just the raw enthalpy values and the different conditions we provided them with. We either increased sigma, decreased epsilon, increased both, decreased both. So that's what the graph on the left represents. And the graph on the right is just a better visualization of the enthalpy values in between the different density points. And what we came to the conclusion is that epsilon, while it didn't provide too much of a change, we realized we did need to decrease epsilon just because we would get a shallower slope, and that is what we're looking for. However, for sigma, we're probably going to have to go back to the drawing board because while decreasing sigma is probably the way to go, we don't know exactly how much we have to decrease sigma now. So we're probably going to have to run a couple more simulations with the CO2 molecules to make sure that the force field is fully finalized. But for our next step, we're just going to keep running these simulations, trying to tweak sigma and epsilon to make sure we are exactly where we need to be and finalize our force field parameters. And then we're going to begin by simulating with actual cannabinoid molecules. Are there any questions?
Which co-solvents are you hoping to be using in the future?
So we are going to start, actually this image kind of represents it. This is an image of a THC with 2 ethanols acting as the solvent. So we're going to start with ethanol and a couple of different cannabinoids, and then past that we'll see what those results yield and then pick new ones after that, depending on what we get.
How do you choose how large of a simulation to run? Like, how many molecules do you go with?
So initially what we've been doing is running the simulations with 1,000 molecules, but the way Boxstart loads them in is that they'll load them in on top of each other sometimes. So what we have to do is minimize the energy. And whenever we minimize the energy, sometimes it separates the molecules, but sometimes it just has to take some of the molecules out of the simulation. So by loading it in with 1,000, it gives us still a good idea of how these molecules are reacting in the supercritical force field. So we have enough molecules left over to actually get some good results.
I was wondering if you'd run into any problems when conducting these simulations.
Other than my learning curve of not knowing how this program works, the simulations, the biggest problems we ran into was those distance-dependent dielectrics I mentioned earlier, just because we weren't getting the results we needed and we weren't sure why we weren't getting those results that we needed. So once we fixed the